Hi everyone. Today I have something very special for you, my highlight of 2024. With an impressive speed of up to 1000 millimeters per second and an acceleration of an unbelievable 100,000 millimeters per second squared, this printer sets new standards. Yes, you heard it right. This Cartesian printer delivers a performance that puts even high-end models in the shade. Today, we'll not only take a look at the construction of this powerhouse, but also how its print results perform in practice. You don't want to miss out on what this printer is really capable of and why it makes the competition look old. First of all, a small introduction. This printer is an open source project where you can source the individual components yourself. For those of you who prefer to buy a complete kit, I can recommend the kit from Fysetc. This kit was made available to us for this video and is currently available on AliExpress for just under 800 euros with discount from the Spanish warehouse. In contrast to the previous Fysetc kits, these sets contain almost exclusively brand components, such as a Dragon high-flow hot end, a Meanwell power supply unit, and a CNC manufactured Sherpa. These high-quality components ensure optimized performance and reliability of the printer. If you would like to find out more about the kit, take a look at our live stream in which we showed the unboxing. You can find the link in the video description down below. Let's take a look at the design first. This little masterpiece comes from LH, a passionate 3D printing enthusiast from Iceland who has put all his experience in this project. This printer is basically built like a classic bed slinger, similar to an Ender 3 or an Anycubic Cobra. This means that the print bed moves in the Y direction while the printhead moves in the X and Z directions. The Z axis is even operated with two belts and separate motors. On the Y-axis, however, two motors ensure that the 9mm thick belt gets plenty of power. The X-axis is driven by a single motor, but with a small modification, a second motor can also be retrofitted here to increase the performance even further. In contrast to the cheaper printers, the frame of this model has been reinforced to the maximum, while at the same price the moving parts have been reduced to a minimum weight. This can be seen particularly impressively in the lightweight printhead, which only contains the minimum amount of plastic necessary to fix the components precisely. This minimalist approach ensures faster and more stable movement of the printhead. The real highlight is the print bed. The frame is made entirely out of carbon, a material that is not only extremely light but also incredibly stable. Equally impressive is the ultra-thin heating bed, which also consists of a carbon plate. In contrast to the usual printers, which use magnetic foils with PE sheets, this model deliberately does without them. Why? Because such a construction would unnecessarily increase the weight of the print bed and could therefore have a negative impact on printing speed and precision. Instead, you print directly on the carbon or use Kapton tape to cover the print surface. You may have already noticed the construction on the gantry. Two huge 9733 fans are installed here, which together with the two 5015 radial fans ensure that the top layer of your prints is cooled at lightning speed. This additional cooling capacity is particularly important at the high printing speeds to prevent deformation and overheating. What particularly impresses me is the sophisticated design of the air flaps. As the docking station for the level sensor is lower than the print bed, the flaps have to be retracted as required. The whole thing is solved by a clever spring mechanism that adjusts automatically, a real ingenious detail. When it comes to the level sensor, this printer uses a kind of a clicky probe. This innovative solution involves placing the probe in a special mount next to the print bed. As soon as a leveling process is required, the probe is fixed to the printhead by magnets and then safely stowed away again in its dock. This not only ensures accurate and fast bed leveling, but also further reduces the weight of the printhead. Let's move on to the question of how the printer is actually supplied with power and control signals. On the back of the printer, at the rear left to be precise, there is a breakout board that acts as a central hub. This is where all the cables from the motors, sensors and other components come together. Three thick cables lead from the breakout board to the so-called E-box, which forms the centerpiece of the printer's electronics. This e-box contains all the important electronic components: the control board, a Raspberry Pi, and the power supply units. Yes, you heard it right. The Fysetc L8 Stinger kit operates the X and Y motors with 48 volts instead of the usual 24 volts. This higher voltage ensures significantly stronger performance and more precise motor movements. In addition, the high-performance TMC5160 drivers are installed here, which are far superior to the standard 2020-09 drivers. However, active cooling is necessary for these drivers to work reliably, as you can see here. Access to the components in the e-box is cleverly designed. A flap allows easy access, but only to the low voltage components. The mains voltage is safely housed at the back of the box and can only be accessed by opening the cover with screws. I find this safety measure particularly successful as it prevents accidental access to the live parts. What I particularly like about this e-box is its flexibility. The box can be completely separated from the printer and transported separately in just 3 easy steps. If you think ahead, you can also use the combination of ebooks and breakout board for other DIY printing projects. So if you ever design your own printer, keep the e-box idea in mind. It could save you a lot of work and makes the whole setup incredibly modular and versatile. Before we look at the test prints and printing times, we need to address an important point. Many printer manufacturers advertise high speeds and acceleration rates in their ads. However, these values are often not realistic as they are usually not taken into account in the slicer settings. But why is this the case? Although these advertised speeds and accelerations can be achieved mechanically, the actual print speed is often limited by other parameters. This means that you must first determine the mechanical limits of your printer. By this, I mean the maximum movement speed that can be maintained without any loss of speed. We have created a script for this. You can find the video for the script in our description down below. First, flow rate. This is defined under the filament settings in your slicer. It specifies how many cubic millimeters per second can be extruded through the hot end. If this value is exceeded due to a large line width, the printing speed is automatically reduced. Even if your printer could be mechanically faster, the extrusion rate will limit the actual print speed. Second, layer time. This setting can be found in the cooling section of the slicer. It specifies the minimum time that the print head requires before returning to the same position to ensure that the layer has cooled down sufficiently. The more filament you extrude per second, the longer the layer time should be, as the filament needs more time to cool down. If some layers only contain a few lines, the printer will slow down considerably to ensure cooling. Third, square corner velocity, also known as jerk. The jerk defines how quickly the print head can change direction without having to accelerate. This setting is often neglected by many printers, but plays a particularly important role in high-speed printing. A good example is the gyroid infill pattern, where the direction changes quickly. If the jerk is set too low, the printer is slowed down considerably during the directional changes. A higher jerk value enables fast direction changes without drastically reducing the speed. 4. Minimum cruise ratio. This setting defines how long a movement must be carried out at a constant speed, which can limit the printer below the target speed. If the distance or movement is too short or the acceleration is too slow, the speed is automatically reduced to ensure a smooth movement in the center of the layer. Especially with small parts or fast movements between infill and perimeter, this setting can noticeably reduce the speed. Just a small addition regarding to the terms jerk and square corner velocity. Clipper uses square corner velocity for its calculations, and this term is also adjusted beforehand. However, to be precise, the term jerk is incorrect when using Clipper because the calculation behind square corner velocity in Clipper is different from the jerk in Marlin. If you consider these factors and adjust the settings accordingly, you can better optimize your printer and achieve realistic printing speeds. In my upcoming test prints, I will always display the settings I used on the side and, in some cases, compare them with my Voron 2.4 so you can see how fast the LH Stinger is in certain areas or with specific objects. For my tests, I used the official LH print profiles provided on GitHub for this project. Don't worry, I will show you a bit more about that in the end of the video. Importantly, I did not manually calibrate any filament settings. Instead, I simply used the generic filament profile and the speed and daily modes beforehand. I deliberately did not make any adjustments to retract, pressure advance or other settings. My idea behind this was to show you the print quality you can expect straight out of the box, the true plug-and print experience. Some of you surely remember the frustration with other printers where it took hours or even days before the first object was finally printed in good quality. To check the assembly and the axis squareness of the printer, I printed a Califlower Test. This special test object is perfect for detecting distortions in the axis through various checkpoints. I also printed the flower using the speed profile. Here, it's less about optic quality and more about dimensional accuracy, which can be precisely analyzed using this sublight Excel table. My results are shown here. The maximum deviation was just 0.3 millimeters. This shows that the dimensional accuracy and squareness of the printer are nearly perfect. Despite the high printing speed, the printer remains precise and stable, which is absolutely convincing in this category. First, I printed the Orca Slicer test object using the LH Stinger speed profile, with a speed of 600 mm per second and an acceleration of 30,000 mm per square second. The jerk is set in the clipper configuration and is 15. I need 1 hour and 36 minutes for this object. For comparison, even if you can't directly compare these values, my Voron 2.4, which is my main printer, took 2 hours and 9 minutes at a speed of 250 mm per second and only 5000 mm per square second acceleration. The reason for this low acceleration is that I want to maximize layer adhesion while also considering aesthetics. Let's take a look at the object. We will start with the dimensional accuracy test. This is the front area where you can pull out small cylinders to check if there is enough clearance to the walls. Here, all 5 cylinders can be easily pulled out, so this test is passed. Now, looking around the object, we have various tests. Bridging overhangs on top, a retract test, and on the side an overhang test with large bridging. Looking at all the walls here, you can't see any significant artifacts. The layer stacking turned out very well. If you see some shadow cubes here, it's simply due to my studio lighting. In the cool white light, you can see almost all artifacts which are usually not visible under normal sunlight. I'm impressed with the overhang test. Even with an overhang of 15 degrees, the layers below are still printed cleanly. This is also thanks to the enormous cooling of the LH Stinger, and you can compare here, my Voron 2.4 wouldn't have been able to print this object better in double the time, even at the slower speed. Thus, the LH Stinger wins this test here. Even though Abstract Flow could print it in a few minutes, I limited myself to slightly adjust the standard profile by setting the layer time to 0 and the jerk to 75. This means that only the hot end with its 50 cubic millimeters per second flow is the limiting factor. Looking at the printed object, which was done in 11 minutes, I can definitely rate the quality as good. There are some inaccuracies here and there, especially on the bottom and the top layers. But that's again because I just used a standard ABS profile here and thus the top and bottom layers suffered due to the uncalibrated flow. My next print was a tolerance test in the form of a fidget spinner. In this model, individual elements are integrated with increasingly smaller gaps to check whether tolerances are precisely maintained. As you can see here, all areas with gaps from 0.15 to 0.55 millimeters can be moved effortlessly. This shows that the printer works reliably even with tight tolerances. The test was also printed using the speed profile and the print time was 27 minutes. In comparison, my Voron 2.4 would have needed about 1 hour and 30 minutes for the same model using the daily profile. The tolerance test is therefore clearly passed and at these impressive speeds. However, you can again see the uncalibrated filament on the top layer, particularly noticeable on this layer. The King-Kroon PLA shows no other irregularities. In particular, the layer stacking has turned out very well. Next, I took on the PCTG from Extruder. This filament particularly known for its flexibility and impact resistance, and what better way to test that than with a model that has a snap mechanism, in this case, pliers. Here too, the print quality and the speed profile absolutely convinced me. Despite the high speed and the print time of just under 7 minutes for the entire print, the result was astonishingly precise. The pliers work flawlessly, the snap mechanism closed cleanly, and the flexibility of the PCTG comes fully into its own. Next, I printed an overhang and retract test, which is a dodecahedron, and it requires very good part cooling to deliver good results. I choose the Extruder NX2 PLA in brown, and you can see from these results that the LH Stinger has no problems with that. This is due to the high quality and effective part cooling, especially with the external fans. To really push the overhangs to the limit, I printed this Saturn model as the next test. This print would have been finished on my Roron 2.4 in about 41 minutes, but the Stinger managed it in 24 minutes. The difference in print time is somewhat smaller here because LH profiles automatically reduce the speed for extreme overhangs to optimize print quality. Looking at the results more closely, you can see some artifacts on the underside even in this extreme test. Unfortunately, the C seam is also not perfect, which again is due to the lack of calibration of the printer. Despite this, you have to consider that we are printing at the absolute limits here, and for that, the results are still remarkable overall. Next, I printed a design test object that was specifically developed to test various difficulties. This model places high demands on the printer, especially due to the complex geometry and the associated different layers, which often leads to visible color nuances on the outer shell during fast prints. For this print, I used a high flow of about 50 cubic millimeters per second, which means that the print temperature for PLA is significantly higher, namely between 230 and 250 degrees Celsius instead of the usual 200 Celsius. Normally, this isn't a problem at such flow rates, but if the object has slow layers, such as the overhang layers here, the filament is overheated, which in the case of King-Kroon PLA has led to a slightly glossy outer surface. This shows that it's especially important with design models to keep the flow rates as constant as possible to achieve a uniform finish on the outer shell. With other filament colors, this effect can become even more noticeable as the saturation and color depth can vary depending on the print temperature. Of course, a benchy must not be missing. I printed this iconic model in just 11 minutes. For comparison, my Roron would have taken about 40 minutes. These 11 minutes were only necessary because I set a fixed layer time of at least 2 seconds to sufficiently cool the red King-Kroon PLA. This longer layer time is particularly noticeable in the chimney, not only in the associated higher print time, but also in the significantly better print quality. By extending the cooling time, I was able to print the details of the chimney cleanly and precisely without having to accept any loss in quality. However, it also shows here that the lower cooling and high speed on the first layers lead to a slightly glossy outer surface. Particularly noticeable here in the change in color saturation, which is directly related to the printing speed. These differences are due to the transition between infill layers, solid layers, and top layers. In my last test, I made a few modifications to the profile. I set the layer time to 0 so that it's no longer limited, and I increased the jerk to 75 because according to abstract flow, that's a possible value. I wanted to push it to the maximum here, so to speak. You can see that the torso will still print it well. With this figure, a small inaccuracy on the outer shell isn't so bad because it imitates natural fur. However, where you can see artifacts is on the ears. Here, the layer time is simply far too low, meaning the layers can no longer cool properly and it's printed onto a soft filament, resulting in such unsightly bulges on the underside. Yes, I tried it at the maximum limits. My hot end is the limiting factor here at 50 cubic millimeters per second. For that, I increased all the other values accelerations to a maximum of 100,000 millimeters per square second, speed to a maximum of 1000 millimeters per second, and also the layer time to 0. Up here in the corner, you can see what speeds resulted after slicing due to the limiting hot end, and here you can see the result. Perhaps quite suitable for rapid prototyping, but here you can see that without further calibration of the stepper drivers and the individual filament settings, and perhaps also with a high flow filament instead of a normal filament, even better results can be achieved. But it shows that you need to dial back the settings a bit here. My conclusion about the Stinger in general. For just under 800 euros, you currently get the basis for probably the fastest Cartesian and generally one of the fastest printers currently on the consumer market. As already mentioned in the intro, mechanically impressive values like a speed of 1000 millimeters per second and an acceleration of 100,000 millimeters per square second with a square corner velocity of 75 are achievable. However, it becomes difficult to realize these values in acting printing without intense calibration effort. Not only the motion mechanics but also the hot end must be able to handle these high flow rates and speeds. In particular, the retract and pressure advance at such speeds would overwhelm most of the currently available hot ends. But even the detail profile with 400 millimeters per second at an acceleration of 20,000 millimeters per square second still offers impressive speed and delivers results at the highest level. So, who is this printer suitable for now? I would especially recommend it to people who are advancing their own developments and rely on rapid prototyping. It also is excellent as a basis for those who have specialized in the topic of speed printing and are developing their passion here. After a conversation with LH, there will soon be a suitable enclosure and a kind of mini MMU for the 3 color prints, which will further expand the printer's range of applications. Now to the Fysetc Kit. Especially this printer used here, based on the Fysetc Kit, receives a clear recommendation from me. The kit was complete and the components were consistently high quality, mostly even made from branded components. Especially with the mains voltage parts, it is important to me that components from reputably manufacturers are used. That gives me an additional sense of security and trust. A small deduction in the B grade goes to the decision to supply the screws in plastic bags and not in a sorting box. As a result, you spend about 25% of the total construction time searching for the right screws. It would also be desirable if even in the first batch, the smaller problems described here in the LH issues had been fixed. However, Fysetc has promised to fix these in the future batches. So if you get the kit, you should definitely go through the issues lists after receiving it and check whether the described points have been fixed. All in all, I had a lot of fun with this review and I will see whether this machine will replace my Voron 2.4 as my daily printer in the long term. If you are interested in a long-term test, feel free to write in the comments. We thank you at this point for watching and look forward to see you again in the next video.